Let's just review here of some of the relationships. So we have to watch out for the temperature, and also we have to watch out what the zero and negative means. You know, the negative means something very different for full potentials than what it means for half potentials. And the way you can think about it is in terms of temperature, you know, arbitrary versus absolute zero. However, the cells can go negative. You know, if the cells go negative, that means you just have it backwards. What you predicted, you know, you predicted the electrons should flow left to right, but in fact they flow right to left because you accidentally or got the anode and the cathode swapped. They say accidentally, it might be purposely because you might be trying to recharge it. If you're trying to recharge it, then we need to know what kind of counter voltage. You know, we have to go greater than the voltage. In fact, we have to often go much greater. And that much greater means that there's a little hump that we have to get over. And that little hump is called overpotential. And sometimes the voltage we have to apply is much more than what we calculate. You know, so it might be negative 2.3 volts, but you end up having to place much more than 2.3 volts to get the electrons to go backwards. And that depends on the mechanism, you know, what the mechanism is. If it's a simple mechanism, then it's pretty easy to recharge the battery. But if the mechanism is kind of complicated, where you have to start breaking bonds, you have to start breaking bonds to get everything back to the way it was originally. You know, that hump in breaking the bonds is going to be costly in terms of energy. But we do all our calculations, so we can do E naught under standard conditions. I mean, this is not too difficult. Just rearrange this algebraically over NF. And then we have E under non-standard conditions, which is E naught under standard conditions plus 0.5592 volts over N or Z. You know, N and Z we're going to use interchangeably. Log of Q. This equation is called the what equation? 0.0592 or 0.592? The Nernst equation. Was it 0.0592 or point? It was 0.0592. If we ever forget, it's not hard to derive, because do you know where that number comes from? That comes from R times T divided by F. It comes from RT over F. So we can figure out what it is. R, what's the R value we should use here? The R value is actually 2.303 also, because we had to convert it from natural log to log base 10. And so what is the R value that we use for this? 8.3145. And the units for this? Joules per mole Kelvin. And then T is in Kelvin. But, you know, normally temperature can vary, but for batteries we don't want them to get too hot or too cold. So we try to just operate them at what temperature? 298 Kelvin, 298.15. Let me add that in there. That's going to change a little bit. 25 degrees C or 298.15 Kelvin. And then the Faraday, you don't have to memorize this. 96,485. what are the units for the Faraday constant. Coulombs per mole of electrons. This Faraday constant's easy to derive. You know how you derive it? You take Avogadro's number and multiply it by the charge on an electron. You know, the charge on an electron is -1 fundamental unit, and the fundamental unit is 1.67 times 10 to the minus whatever coulombs. I think 10 to the minus 18 or 10 to the minus 19 coulombs. I had it memorized when it was in physics, but forgotten it. And so it's not hard to derive. We know the charge on a single electron, and if we have a mole of them, we just multiply by Avogadro's number. We can get this number if we ever forget it. But the units don't appear to work out. Do you see the units don't look like they work out? Because when I look at this, the Kelvin cancels, the moles cancel, but joules and coulomb don't seem to cancel. And that's because you can write joules is a unit of energy, and you can write this in different forms. So, for example, joule can be written in liters atmosphere when we're doing PV work. You know, it's like 101.3 joules per 1 liter atmosphere. You know, so if you blow up a 1 liter balloon against the external pressure of 1 atmosphere, you've just used up 101.3 joules of work, right? But there's also work in pushing electrons or pulling electrons through an external circuit. How much work do you have to do to pull electrons through an external circuit? Well, it's going to depend on the volts, that is the force, right? How much force do you have to push or pull on the electrons to get them through that circuit? And it's also going to depend on how many electrons there are, right? In terms of, and one way of figuring out the number of electrons that are involved is via coulombs. You know, the more coulombs of charge, the more electrons, according to Faraday here. And so the amount of work is going to depend on how much and how forceful you need to get those electrons through. And so if a joule is equal to a volt times a coulomb, what cancels? The coulombs cancel, and that leaves us with units of volts. And so this is why I wrote volts here. Is it 0.0592 or is it 0.592? And so I can just figure it out here. We can verify that 2.303 times 8.3145 times 298.15 divided by 96,485. And did I get the 2.03? Yes. 0.059. So I made a mistake here. It should be 0.059. And I only want to memorize 1, right? Or know how to derive 1. So I'm not going to bother remembering the natural log, which is 0.029 something. I'll just remember 0.0592 volts. But you don't have to remember that. That's going to be a given. But you know, you should know how it's derived here. And so we can calculate the cell potential at any concentration. That is, at any extent of reaction. You know, because the concentrations are going to depend on the extent, how much reactions occurred. You know, when half of it has reacted, what's the voltage? Is the voltage going to be 1/2 the original voltage? What do you suspect? No, it's not going to be. When half of it's reacted, it's not going to be half the voltage. There are other kind of tricky things, you know. when we're looking at half-cell potentials aren't additive, you know, like delta G's. You know Hess's law? Hess's law doesn't apply to E, these E's on the right side here. Hess's law doesn't apply to these E's here. Or I guess it does. It looks like it applies. You know, we take the anode plus the cathode. We take those two half reactions, we add the E's, right? But when we're trying to do that to, let's say, reduction potentials, let's say I want to know the reduction potential. Let's just look at an example here. Let's go to copper. And take a look at the reduction potential. Maybe it is additive. Let's see if it's additive. One thing we could do with copper is we can go from let's see if I have it here. We can go from copper metal here all the way to copper 2+. And that's 0.34 volts. Negative, because if we go from copper to copper 2+, we need to reverse this. Reversing this is negative. But what we could do is this as well. We can go from copper metal to copper 1, and then from copper 1 to copper 2. Here's copper 1 to copper 2, the top. That would be negative 0.159 volts. And what about copper metal to copper 1? See if I have that here. Wow, this is weird. Here it is. It's 0.52 volts, negative. And so 0.52 plus, where's the other copper? Not too many entries in this table. This table is quite a bit bigger. Plus, here, this one, down to 0.159. So let's do that. 0.159 plus, that's copper 1 going to copper 2, and then we want copper metal going to copper 1. And so where was that? Here it is. No, that's not it. Copper, here it is. Right about there. 0.52. And so that gives me 0.679 volts. So if I go from copper to copper 1, and then copper 1 to copper 2, and I add those two, like Hess's law, I get a total of 0.679 negative. Whereas if I just go from copper metal straight to copper 2, so copper metal straight to copper 2, what does that come out to? 0.34 volts, a huge mismatch. Do you see that? And so the point of that is what we can do is we could add up the delta G's, and then we add up the delta G's and then we convert it into an E. And so the delta G's are additive according to Hess's law, but the E's aren't. The E's behave a little bit differently. Remember, energies are extensive, but these are intensive. And so they don't quite add up like you expect them to. Also, when we multiply by coefficient, it doesn't change anything. You know, when you multiply by coefficient, delta H's, delta G's, delta S's, it changes. And so you have to be careful. We treat, you know, in certain respects, it seems similar because we have all these equations, delta G, E, etc., K. K is not, you know, difficult to figure out if we know delta G. So we could relate it to K. I mean, delta G naught is equal to minus RT ln of K. And so we have all the thermo equations there. You can map out if you want. All right. So we looked at some applications, you know, concentration cells with a pH meter, measuring K, like KSP. You know, KSP measurement, we could do measuring the voltage, because we're going to relate the voltage here to K directly. And we can relate it to delta G as well, because the higher the voltage, the more negative the delta G is going to be, and the more spontaneous we expect the process to be. A negative cell voltage means we're going to have a positive delta G, which means the reverse reaction is favorable. So the cell voltage is directly related to the driving force here. All right, the other thing that we're going to look at is corrosion. So let's take a look at corrosion here in the book. Corrosion they call unwanted voltaic cells. You know, rusting is actually a voltaic cell, electrochemical cell. Rusting of iron. Normally we think of rusting of iron as just iron being oxidized. And so when I think about rust, I just think about this. You know, rust is Fe2O3, and so if I have iron and 2 irons, and I need 3 oxygens, so I'll take 3 halves O2 gas, and I go, this is going to produce Fe2O3 rust, solid. But it's not so simple as this. If this were the case, then you know, iron would be a lot more stable than it is, but it corrodes rapidly. It turns out it's a bit more complicated. And so let's take a look at a piece of iron. Let's look at an iron nail. Actually, we're going to take an iron nail and then bend it like this. Do you know that the iron, all the surface iron atoms don't have the same energy? We call this the surface free energy. And the higher the surface free energy, the less stable. And so when you look at the surface of a nail, which iron atoms would be the least stable? It's like a sugar cube. Do you know all the sugar molecules in a sugar cube don't have the same energy on the surface? Which one are the highest surface free energy sugar molecules in a sugar cube? Right, at the very corner. If you have a sugar cube, what is going to happen is the highest energy sugar molecules will dissolve first. And those happen to be right at the corner. Why are those the least stable? Because they're just barely hanging on. You know, just think if you're the last one at the tip of the corner there, you know, you're all exposed in space. Versus the ones that are comfortable inside. We have bulk. The bulk are the least, have the least surface free energy. And then we have the ones on the face. Those ones are going to have higher. And then we have the ones on the edge. Those are higher. And then we have the ones on the corner. Those are the highest. inner surface. Does that make sense, pretty much? Yeah. And so the one at the point here is going to be easy to react, and the ones on the edges here are going to be easier to react. And then if we put a bend here, not only that, let's hammer this down. We're going to hammer it and then put a bend here. When we hammer it, we introduce surface defects, that is ledges and all kinds of other stuff, that we can see. And that that's going to create less stable lattice. And this less stable lattice is more susceptible to attack. And so if you ever have a car and you get in an accident and the fender gets creased, you know where it's going to start to rust first? Right at the crease, because you created some defects there. Those defects will be attacked. And so if you're an oxidizer, which iron atoms will you attack first? The ones that are least stable. So if I'm an oxidizer, I'm going to come in here. Let's say I'm oxygen. I'm going to come in here and I'm going to attack these irons here. And if I attack those irons, then I'm going to oxidize the irons. And what do we call that when we have oxidation? Is oxidation the anode or the cathode? It's the anode. And so this part of the iron nail we call the anode. And so basically the anode is going to get oxidized, and we're going to produce iron 2. We don't go all the way to iron 3. You would think so, but it doesn't. It initially just goes to iron 2 because that's the path of least resistance to go to iron 2. But iron 2 is not going to live for very long because eventually iron 2 will be converted into iron 3. But that's going to take a little bit more time. But where did the electrons go? Well, actually, the oxygen doesn't have to attack here. It could attack here. Instead, what we could have is this. Let's say the oxygen didn't attack here. Let's say the oxygen attacked here. If the oxygen attacks here, then the oxygen will be reduced. Now, the oxygen is going to be reduced to what? It's going to be reduced to oxide. But is oxide very stable? We're going to have oxide ions on the surface of this. Are the oxides very stable? No. They aren't. They're terribly unstable. But that's what we need. Now we need the oxides to migrate over to the iron, or the iron to migrate over to the oxide. Which one will migrate faster, oxide or iron? Oxide. It weighs a lot less. And so the oxides are going to migrate towards the iron, and then we're going to get rust. What would be really helpful here? If we had, this is going to be very slow, isn't it? What would be helpful is if we had a salt bridge to help neutralize the space charge. Not only that, if we had a salt bridge, is oxide stable in water? No. Actually, it's not stable in water. What's going to happen is the oxide is immediately going to attack the water. So we're just going to add water in here with the oxygen. So we're going to have oxygen plus water. And instead of making oxide, what would be a lot more stable? Hydroxide. So rather than making oxide, we're going to make hydroxide. But we need water. If there's no water around, are we going to see much appreciable rust? No, we're not. And so it's got to be wet. Not only that, wouldn't it be better? Because if there's water around, it's still going to take time for the hydroxide to migrate over to the iron 2. That's still going to take time. And therefore, we're going to build up space charge, but that space charge is going to dissipate as the hydroxides migrate towards the iron 2. When the hydroxides come into contact with iron 2, do you know what happens? When the hydroxides eventually make it to the iron 2, we're going to form a precipitate of iron 2 hydroxide. Do you know what color iron 2 hydroxide is? It's green. Iron 2 hydroxide is actually green. But if we had a salt, and if we had salty water, you know, this is going to happen a lot faster. It's like, you know, when you put the salt bridge in there, boom, we got voltage. Well, without a salt bridge, you know, you barely have a trickle. Does that make sense? And so the electrons actually are going to travel from the anode to the cathode here. And so we got but that's not a problem because this is an iron nail. And so it's kind of weird because the anode and the cathode are made of the same thing. In fact, they are the same thing. It's an iron nail. But the anode is going to be where the defects are. And so this turns out to be an electrochemical process. And the electrochemical process is this. We have iron metal going to iron 2 plus 2 electrons. So this is the oxidation half reaction, or the anode half reaction. And then over at the cathode, it depends. So for example, if we have oxygen and water, we're going to form hydroxides. 2 hydroxides, it looks like. I need to tweak this. I'm going to put 2 waters here. So oxygen plus 2 water is going to make 2 hydroxides, and then we'll be left with, and a water. I guess I could get rid of one of those. I'll need to balance this. Rather than going 2, I should have probably just went 1/2, and then, but I'll make 4 hydroxides here instead. And that should be all right. Okay. But do you know, if I had acid, I could make something even more stable? If I had acid, what could I form? Rather than just water. If I had acid present, then is hydroxide stable in acid? No. Hydroxide would be neutralized by the acid, forming what? Water, an even more stable product. So if there's acid around, then corrosion should be even more favorable because it forms an even more stable product. And so certain things will boost corrosion. One, water for sure. We need water, moisture. And so if you have dry iron, it's going to be very slow corrosion. 2, salt water. If we have salt water, then corrosion is going to be a lot faster because we can eliminate the space charge immediately. And 3, low pH, acid. Acid will help enhance corrosion. And so if you want to protect your iron from corroding, keep it dry in an acid-free environment with no salt around. Then it could last. And so let's look at the net reaction here. How many electrons does this have to gain? And so these are already 2 minus, so this has got to gain 4 electrons. And so let's combine these 2 half reactions. The top one I'm going to multiply by 2. And so the corrosion is actually a bit more complicated than the equation I just wrote up there. This is the corrosion in water. If I do this in salt water, it's the same equation. We just eliminate the space charge. If I do it in acid, I get a different equation. In acid, I get the O2 plus 4H plus equation. And so we'll have 2 irons plus an O2 plus 2H2O liquids. This is going to go to Fe2 plus 4 hydroxides. Fe2 plus 4 hydroxides, this is going to undergo a metathesis reaction. The metathesis reaction is going to produce 2FeOH2 solid precipitates. But that metathesis reaction, the Fe2 plus is produced in one area, but the hydroxide is produced in another, so there's going to be a delayed precipitation. We have to wait for the hydroxide to migrate, and then we'll precipitate. This looks a lot more complicated than this. You know, in my original corrosion reaction, I just had iron reacting with oxygen. And this could happen, I suppose. You know, it just happens slowly. All right, so let's take a look at what they did here. In A, they hammered the ends of the nail. Do you see that? Flat. Just took a hammer and beat it down. If you take a hammer and beat it down, what are you doing to the crystal structure of that? You know, the iron nail is made up of a whole bunch of little crystals of iron that are pretty much clumped together, but they're clumped very well. They're strongly, we call it sintered. They're sintered together, so they're kind of melted together. If you hammer the ends of the nail, what are you going to create? Defects. And so the ends of the nail are what we call the anode or the cathode. Anode. We have two anodes here. And do you see this purple here? You know what that purple is? You know what they put in here? Phenolphthalein. And phenolphthalein detects what? Yeah, hydroxide. And so the center of the nail is what we call the cathode. And so the oxygen comes in here, plucks the electrons off the cathode and forms hydroxide. But it takes time for the hydroxide to migrate to the iron 2. Look carefully here. Do you see a little fuzz on here? This is poor resolution. I thought they would have better resolution than this. But do you see the green fuzz on there? You know what that green fuzz is? Yeah, iron 2 hydroxide precipitate. And the hydroxide diffuses much more rapidly than iron 2, so iron 2 has barely moved and hydroxide's already attacked it, but still it takes hydroxide some time to get there. Okay, let's look at this next Petri dish. Do you see what happened here? They took a nail and then bent it and then hammered the ends. And so how many anodes do you see and how many cathodes do you see here? Yeah, 3 anodes, 2 cathodes. The cathodes still look pristine, but the anodes are starting to look pretty corroded. Yeah. Eventually it runs out of defective iron and this starts attacking the normal iron, you know, and the whole thing will rust. But here you can see the precipitate a little bit more clearly. There's a lot of green precipitate there. Here. Here they left the nail pristine. But instead, you know what they did? Do you see this gray stuff here? This zinc foil. They just wrap this with zinc. So if you wrap it with zinc, who's going to get oxidized? Well, the species with the highest oxidation potential will be oxidized. And so what has a higher oxidation potential, zinc or iron? The zinc has a higher oxidation potential. And so what's happening now is this. The zinc is going to be the anode. That's where we're going to corrode. And so, and the nail itself will be, the whole nail is going to be the cathode. Because zinc is a lot easier to oxidize. Zinc is also a heavy atom, so it moves sluggishly. But do you see the precipitate around here? What color is that precipitate? It's actually white here. Do you see the white precipitate there? That's zinc hydroxide. Zinc hydroxide is a white precipitate. Okay, you know what they're doing here? They took our nail, but they wrapped it in copper. So which one has a higher oxidation potential? Copper or iron? Iron. Iron has a higher oxidation potential, so the species that's most likely to be oxidized is the one with the highest oxidation potential, iron. And so in this case, the whole iron nail is the anode, and the cathode will be all the copper. Do you see the entire thing is the cathode here? This whole thing is going to generate hydroxide, and eventually the hydroxide is going to migrate to the iron and precipitate out this green precipitate, which is the iron 2 hydroxide. The electromagnet they use copper because copper is an excellent conductor of electricity. You can make electromagnets out of any metal wire if you put twists in it. That's it. And it's fairly resistant to corrosion. But you can make out of gold wire if you want, platinum wire. That would be even less resistant to corrosion. It'd just be really expensive. So if your iron nails are holding up your house, then what you want to do is you want to prevent them from corroding. And so zinc seems to be an excellent way of preventing corrosion. And in fact, you can buy two kinds of nails. You can just buy regular iron nails, or you can buy something called galvanized iron nails. And you know, in the galvanization process, you know what they do is they just dip them in molten zinc. And when they pull them out, there's a coating of zinc around the nail. And so this way, if your house is built with galvanized nails, then what's going to corrode is the zinc. The zinc is not a structural metal. You know, the iron is the structural metal, and so it protects the iron underneath the zinc. The only problem is this. You have to have excess zinc. Pretty soon you're going to run out of the zinc due to just normal corrosion processes. And when you run out of the zinc, what corrodes next? Well, the species with the highest oxidation potential, and there's no more zinc, it's going to be iron. And so the iron will start to corrode. This type of protection, galvanized nails, is called a sacrificial anode. We don't care about this anode, the zinc anode, because it's not structural. And zinc is not so expensive. Zinc is pretty cheap. And so we're going to just sacrifice the zinc here. The Statue of Liberty has a steel frame that's coated with copper, but the copper is not structural. And so all the structural steel is being eaten away there. So, and all you're left with is a hollow film of copper metal, which cannot support the Statue of Liberty. So and the steel's being replaced there. And so this would be like the Statue of Liberty. The sacrificial anode in this case is the important stuff.
That's why the Statue of Liberty is burning.
Yeah. Yeah, when I went to New York, it was closed for... But, so didn't get to go out there. Anyway, yeah, it's green. There's green also from copper as well. Copper can react with sulfur in air and create sulfate, so like copper 2 sulfate and those, which are blue but they look green, you know. And so the copper itself can get corroded as well. And so here, once all the iron's gone, then the copper will be the next species with the highest, you know. But oxidation potential. And so there are different ways we can protect the nail. One is if we make sure we completely seal it. That is, if we paint it. If we paint it, then no oxygen can attack the iron here. We need oxygen to attack the iron. And so if it's painted, it'll protect it. Or if the copper coating had no nicks or gaps, then the copper coating would work. And that's called putting an inert barrier over it. And so we could put an inert barrier over it. The other way of protecting the iron is the sacrificial anode. So two main ways of protecting iron is to paint it or put a coating. And that's why we have chrome plating over here on our plumbing. Otherwise, it'd be completely corroded. This chrome plating is very good because it's very hard to put nicks in there. If you put a nick and scratch that goes through the entire coating, then it'll start eating it away from the inside, like the Statue of Liberty. Copper isn't as tough a material as chrome, so it doesn't provide the same protection. And the other way of protecting it is by sacrificial anode. We don't have to use zinc. We could use anything with a higher reduction potential or oxidation potential. What do we want? We can use anything with a higher oxidation potential to act as a sacrificial anode. And so there are other metals with higher oxidation potentials. Give me one. Well, maybe without the chart, it's hard. This is galvanized nails with a zinc coating on there. It doesn't matter if there's a scratch or nick here. It's no big deal. If there's a scratch or nick here, this is not a protective coating. This is a sacrificial coating. If you look at the hull of this ship is made out of steel. And if you look at the hull of this, do you see those things that are attached to the hull here? Or not the hull, I don't know what that is, the rudder? Do you see that? Those are blocks of magnesium. And so magnesium has a higher oxidation potential than iron. And therefore, this should work as well. You know, for pipes that are buried underground, you know, those are susceptible to corrosion. So you can buy sacrificial anodes at Home Depot or Lowe's, you know. They sell them for pipes and whatever else. In fact, I need to do this for some iron I have. I think usually you just bury it in the ground and have it in contact, electrical contact with the iron fence or gate or whatever you have. Help prevent it from corroding. I need to do that. It's called sacrificial anode because we want to protect the cathode. And so this type of protection is called cathodic protection, or alternatively sacrificial anode. We're protecting the cathode. Copper is not effective. Copper plated iron, because you have these gaps. Once you have a gap, forget it. But zinc plated iron is good. Here. Other things we do is no salt water, you know, but that's hard to do for a ship. Another thing we do is no acid. Because all those things will help speed up corrosion. But anyway, corrosion is a voltaic cell. Voltaic cells are batteries, so corrosion is an unwanted one, but a wanted voltaic cell is a battery. So let's go back to batteries and let's take a brief survey of the batteries here. Alkaline batteries have gone way down in price. It used to be really expensive. And people would use these, the Lanche dry cell. Let's look at the construction. This is what we call the heavy-duty battery. This is not rechargeable because the reactions involved here are kind of hard to reverse. But it's a very interesting cell. So what we need is we need a oxidizer. And what's the oxidizer here? The oxidizer is at the cathode or at the anode? The oxidizer is at the cathode. So is graphite the oxidizer? It turns out graphite is not the oxidizer. Graphite is what we call an inert electrode. Inert electrode, it's not going to react. The job of an inert electrode is to supply electrons to the oxidizer. So what the heck is the oxidizer here? MnO2. Is MnO2 soluble or insoluble? Insoluble. So how does the MnO2, which is a tiny crystal, travel to the cathode to pick up the electrons? It doesn't. The MnO2 just stays wherever it is. Some MnO2 will be in contact with the cathode, no big deal. But what about the MnO2s that aren't in contact, direct contact with the cathode? How do you get the electrons to jump the gap? And the way you get the electrons to jump the gap is by having carbon black paste. Do you know what carbon black paste is made out of? Carbon. Do you think it's made out of diamond, black diamonds? No. So guess what it's made out of? It could be made out of charcoal, and charcoal is a mix of diamond. Is there diamond in charcoal? No. And so charcoal is a mix of what we call graphitic carbon, or graphite, and amorphous carbon. It's graphite, yeah. And so carbon black paste is just a paste of graphite, little crystals of graphite. And the thing about the carbon black paste is it's an electrical conductor. So the MnO2s don't have to move to it. What you're doing is you're encasing the MnO2 in the graphite itself, but not on the graphite rod or in the graphite rod. You're just making a paste of MnO2 in a graphitic mix. It's a paste, so there is some moisture there. But the job of the paste is to make sure the MnO2 crystals get the electrons. Manganese is, what's the oxidation state of manganese in MnO2? +4. But who's going to lose the electrons? Well, whoever loses electrons, we want to make sure that it has a high oxidation potential, because MnO2 has a pretty high reduction potential. And the higher the reduction potential and the higher the oxidation potential, the greater the voltage we can make in the battery. Right? And so who's going to lose the electrons? Well, I need to scroll down here and then you can see. Is zinc metal. And so the can is not made out of zinc metal. The can is coated with zinc metal on the inside. Zinc is very soft metal. And so this is like a steel can with zinc coated on the inside. And what we need to do is we need to run a wire from the can to the cathode. And then the electrons can travel through an external circuit. And so there's no external circuit here. There is an internal circuit. And when we think about it, we usually have two beakers. But in this case, what we're going to do is we're going to separate the cathode from the anode using this paste. This paste is an electrolyte paste, and this electrolyte paste serves as the salt bridge. So basically. And the salt bridge is going to prevent the MnO2 from oxidizing the zinc directly because this paste isn't a great, well, it can conduct electricity, yes, it can conduct electricity, but it's going to be easier for the electrons to take the external circuit rather than the internal circuit here. And so this paste separates it, and that's our salt bridge, basically. And our salt bridge is going to consist of ammonium chloride and zinc chloride. Ammonium chloride and zinc chloride aren't the cheapest. Why do they use that? There's a reason they use that, and this is very, very impressive. You know, the thinking that went into this battery. Okay, so at the anode, oxidation occurs. So this is the oxidation half reaction. Zinc goes to Zn2+. And then the two electrons, we need to travel through an external circuit. The external circuit could be like a flashlight or whatever you're powering, your phone. Although you wouldn't use this battery to power a phone. Whatever. And then here at the cathode, we have reduction occur. And the MnO2, which is a solid, and there's water present, otherwise we have to form oxide. And, rather than forming oxide, it's better to form hydroxide. And so that's why we have the water to supply hydrogens to form hydroxides rather than oxides. And then we're going to form Mn2O3. So we're going to go from manganese 4 oxide to manganese 3 oxide. In the process, we're going to pick up 2 electrons, you know, for 2 MnO2s. And so this is what's happening. Now, normally a salt bridge does not react. You know, so the job of the salt bridge is to neutralize the space charge, right? But what these people did was they thought, okay, what if we had a reaction? For example, what if we had an acid-base reaction? That is, if we had ammonium ions there, then the ammonium ions could react with the hydroxide ions that are produced and make ammonia gas and water. But you're thinking, why do you want to make ammonia gas? Because if you're making ammonia gas in there, then pressure is going to build up. And as the pressure builds up, then you have to have a stronger and stronger case. Otherwise, the ammonia will leak out. And so, well, then they decided not just ammonium chloride. Chloride's a spectator here. But they're going to put in one other thing, more zinc. Now, zinc's already being produced, but it's being produced all the way at the anode. And it would take a long time to migrate to the cathode. If we have zinc right at the cathode, zinc ion, not zinc metal, if we have zinc ion right at the cathode, then the ammonia that's produced can make the diamine zinc complex. And the diamine zinc complex, zinc 2 complex, is very stable. And I told you chloride was a spectator, but that's not the case. You know, normally chlorides are spectators in metathesis, except for silver, right? But there are other precipitates that precipitate out as chlorides, and one of them happens to be this. So if you have diamine zinc will undergo metathesis reaction with chloride to produce diamine zinc chloride. Now they put all of it in one here. I would do it in 2 steps. First, I'd make the complex, and then I'd precipitate. So the first step is Lewis acid-base reaction. Second step would be the precipitation. Now, why go through all that work, and why even bother? You know, just have a cheap salt bridge. Why do all these reactions? Well, when you add up all these, Hess's law works for that. We're going to add up all these reactions together. And so we'll take the anode reaction, and then we're going to do all these reactions with the other stuff. Did they not add them up? They did not add them up. So let's look at the overall net reaction. The overall net reaction is we're going to add all these reactions together. And so let's just make sure it comes out balanced. So we lose 2 electrons here, we gain 2 electrons here. So we can just add these 2 together. And so the net redox reaction, do that. Try that one more time. I'm going to have to recopy that. I forgot to add more pages here. This is going to copy and paste it, but we'll just write it out since it's better to write it out anyway. So at the anode, we have zinc going to Zn2 plus 2 electrons. And at the cathode, we have MnO2 plus water. We're going to have 2 of these plus 2 electrons. This is going to go to Mn2O3, solid. This is solid. Water is a pure liquid. And how many hydroxides? 2 hydroxides. Yeah. And so the purpose of the water is so we don't have to form oxides. We can form hydroxides. So we'll need some water. This is why there's got to be some water present. It's not totally dry, even though they call the launch a dry cell. It's not completely dry. But it's not totally wet either, like the battery we built earlier. So what we're going to have is Zn solid plus 2 MnO2s solids plus H2O liquid. This is going to go to Zn2 plus Mn2O3 solid plus 2 hydroxides. What's special about pure solids and pure liquids? Remember this symbol here. What was that symbol? Didn't really draw it that great, but it's like an E with a long tail, like this. Remember seeing that symbol? What was that symbol called? I mean, I don't know the name of that symbol, you know, the Greek name or whatever, if it's a Greek one, I don't know. But what it's called, E stands for, kind of looks like an E, and the E stands for extent of what? Extent. Why do we care about the extent of reaction? Who cares how much reaction has progressed? 50% reaction, 75% reaction, 90%. Who cares? Why do we even care what's happening with the extent of reaction? Because when reaction progresses, what happens?
Less efficient.
Yeah, usually when reaction happens, what happens to the voltage? It goes down. Pretty soon it's going to be not zero. Pretty soon it's going to be low enough that it can't power anything. Like, you know, I kind of waste a lot of batteries. I was just going through a whole bunch of batteries. I had a little voltmeter, so I measure the voltage. And so I have some AA's and AAA's. And so I'll just check the voltage. You know, good fresh AA or AAA's, you know, close to 1.6 or 1.6, over 1.6 volts. But when it gets to about 1.4 volts, I have to toss it. 1.4 volts, you're thinking, that's still got a lot of voltage, right? But 1.4 volts isn't enough to power anything. And so I had my remote control, TV remote control. I had to toss the batteries. They were at 1.4 volts. It wasn't enough to power the TV remote. And I wonder how much extended reaction. At what point am I throwing it away? You know, do I have 20% reaction, 30% reaction, 40% reaction? Certainly not over 50% reaction, is it? Seems like I'm wasting a lot. You know, I'm just going from 1.6 to 1.4 volts, and how much reactions occurred during that voltage drop. It turns out a lot. You know, it didn't go down to zero, but I had a lot of reaction occur. And so it wasn't like I'm, you know, wasting a huge amount of resources. Like first world countries, you know, the batteries. Pretty soon batteries are going to be an issue for first world privileged. But anyway, going back to this, what causes voltage to drop as the reaction progresses? Yeah, you build up product and you lose reactant, so Q is getting bigger and bigger. As Q gets bigger and bigger, what was that equation? E of the cell under non-standard conditions is equal to E of the cell under standard conditions plus this correction plus 0.0592 volts over Z log of Q. As Q grows bigger, this becomes more positive and the cell potential goes down, right? Because Q builds up more product. But when we look at Q, Q is equal to the concentration of the products over the concentration of the reactants raised to their respective coefficient. What's special about the concentration of pure solids and pure liquids? Yeah, they don't change. And so the only thing here is we're going to build up the concentration of zinc ions and we're going to build up the concentration of hydroxide. But all these others, the concentration doesn't change. If the concentration doesn't change, the only thing that can happen is we run out. But as long as we have that, then it has the same activity, right? And it should produce the same voltage. And so the only troublesome ones are zinc. Zinc is screwing it up, and hydroxide. And so as zinc and hydroxide build up, then that's going to decrease the voltage. But you think, well, zinc and hydroxide, they'll come together and form a white precipitate, but they have to come from opposite ends of the cell, right? They have to come from opposite ends of the cell. And so it's going to take time. But eventually they'll precipitate and make zinc hydroxide. But we could speed this up. We could speed this up. Well, the salt bridge will just neutralize, you know, the space charge. It doesn't get rid of the ions. But what we can do is, rather than having hydroxide migrate, we can have ammonia gas. What's going to migrate faster, ammonia gas or hydroxide? Ammonia gas. So if we take the hydroxide and react it with ammonium, where's the ammonium coming from? The ammonium is coming from, yeah, ammonium chloride, the salt. And this is going to produce ammonia. And then the ammonia likes zinc. And so the zinc and the ammonia are going to come together to form the diamine zinc ion. And there's chloride present. And did you know that chlorides are all soluble except for silver, lead, mercury, and diamine zinc? Diamine zinc is not that common, so you didn't have to memorize it. But this is going to react with two free chlorides, and then it's going to precipitate out the diamine zinc 2 chloride, solid, PPT. So what's the overall reaction here? Let's go ahead and write that. The overall reaction is going to be this, and this is going to be present. We got lots of this present here. If you have lots of ammonium chloride, and then its concentration doesn't change rapidly, because ammonium chloride is serving two purposes, and ammonium chloride is not so expensive, so we could have lots of it. That's the other way of maintaining relatively constant concentrations, is just have it in huge excess, so you barely use any of it. But the overall reaction is going to be like this. It's going to be zinc plus MnO2 There's H2O liquid plus the ammonium chloride is going to yield, I guess we're going to need two of these. Plus Mn2O3. So this, if we keep this in high concentration, then we don't lose much, and its concentration stays fairly stable. Or we could go with solid. If we went with semi-solid, let's say this was semi-solid, then its concentration doesn't change pretty much at all. And what we've done here is we put all these in terms of pure solids and pure liquids. If we put all these in terms of pure solids and pure liquids, do we have to worry about the extent of reaction so much? No, the voltage is going to be stable. And so the goal of this, why they did all this, was to create a stable voltage. Once we run out, because eventually we're going to run out, then the voltage will change. So as far as throwing out the battery at 1.4 volts, the extent of reaction was actually quite large because of this. But that was an alkaline battery. I don't buy really these heavy-duty batteries anymore, the launch dry cell. I use the alkaline battery. And so what's the difference between an alkaline battery? Well, they're more expensive. Alkaline batteries are more expensive, and they last longer. Do they last longer? Yeah, they last a lot longer. So a superior form of the Lange cell is the alkaline cell, which uses sodium hydroxide or potassium hydroxide in place of ammonium chloride. Well, they're more expensive because sodium hydroxide and potassium hydroxide are more expensive. They're more reactive, so they're more difficult to make, probably. I don't know. Or there's just a better profit margin. And so if we use sodium hydroxide or potassium hydroxide in place of ammonium chloride, what's going to happen? What's going to happen is this. We don't have to generate ammonia. We don't have to make this weird complex precipitate. We can just generate zinc hydroxide immediately. So when zinc ion is produced, it's going to precipitate out zinc hydroxide, solid. And therefore, what we're going to get is we're going to get this all in terms of pure solids and pure liquids. The advantages of the alkaline cell are that zinc does not dissolve as readily in basic alkaline medium as acidic medium, and the cell does a better job of maintaining its voltage as currents drawn from it. How long have I been talking now? Way too long. Okay, any questions on this? These generate 1.5 volts here, both. So.
Is it called alkaline because of the ammonia?
No, there's no ammonia in the alkaline cell. In the other cell, there's ammonium, which gets converted to ammonia, which would be acidic. it's called alkaline because they have to add alkali. Alkali or would be like lye. Lye is the classic alkali, which is sodium hydroxide. You can buy that at the supermarket. It's not so cheap. Lye. In fact, lies. They use lye for many different things. For example, soap making, they use lye for that. And so in Utah, they have lye being mined there. I think there's some natural deposits of lye. But if you have to make it, it's expensive, I suppose. And so they call it an alkaline cell because of the alkaline electrolyte that they're using here. It's still a gel, though. I mean, it's that. Versus lead acid storage battery. A lead acid storage battery has this liquid acid in here. It makes it heavy. Water is pretty heavy. A gallon of water weighs, do you know how much a gallon of water weighs? Like 8 pounds. I never checked. I did check it. As if you go like backpacking or something like that, and there's no water for a long time, then you got to carry it. And you got to carry it. It starts to become very heavy, especially living in desert type areas like Southern California. It's very heavy. So I was carrying 3 gallons of water, 24 pounds just of water. But these batteries, I don't know if you've ever picked up a car battery. They're really heavy. Not just because of the water, but also because of the lead. There's a bunch of lead in there, and lead is a very dense metal. A lead acid battery like this has 6 cells in here connected in series. Each cell makes about 2 volts. And so if you have 6 of them, the total comes out to 12 volts. And so we can make a 12-volt battery by having 6 cells. And you can see it here, because this is an old-style lead-acid battery. And do you see these caps here? You can get a coin and unscrew the caps. You have to unscrew the caps because you have to fill this with water. Sometimes the water evaporates off, but the water is actually consumed in the reaction as well when you recharge it. I'll talk about that. And so these batteries have to be maintained. So every whatever interval, you have to unscrew all of these and add deionized water. Otherwise, the electrolyte level gets too low. Not only that, you have to make sure it has the right acidity. It doesn't quite have enough sulfuric acid, and you have to adjust that as well. And so people, you know how they check for acidity here? They don't drop a pH meter in here. Do you know what they do? They check the density. Sulfuric acid is pretty dense. It's like syrup sometimes if it's concentrated enough. So they check something called specific gravity. Specific gravity is the density of it. And if it's within range, then it's good. If it's out of range, then it could be nearing the end of the life of the battery. Time to replace it. Well, lead has a pretty good oxidation potential. So lead is the anode. What's the cathode? Yeah, lead-4 oxide. Lead-4 ions are pretty good oxidizers. But lead-4 oxide is not a good conductor. So the cathode is in this matrix of lead here. And so rather than having black carbon paste, we have lead. And lead is going to supply the electrons to the solid. This is solid oxide. They say here, the photo on the left shows a typical car battery which is composed of 6 cells in parallel. Is that right? If I connect 6 cells in parallel, do the cells add up? No. So this should have been 6 cells in cells. Not parallel. What's the other way of connecting the cells? Series. So this is wrong. It's easy, you know, when you have a lot of stuff, it's easy to make mistakes. This is the whole purpose of peer review. So, and sometimes you don't see the mistake because in your mind you already have things labeled. And so on the test, which is I'm going to hand back, Colin mentioned one of the problems was wrong. And I swapped it. I was saying this is the pKa, and that was the desired pH. I just got it backwards twice. I don't know why. I kept thinking that. But then I looked at it and I go, wait, that can't be right. Because the pH is higher. You got to have more base. But anyway, there are a number of errors in this book, but I won't point them out. If we look at the battery here, take a look here. The reduction half reactions at the cathode or the anode? Cathode. And the oxidation half reaction is at the anode. And so what are we oxidizing? We're oxidizing lead. But rather than forming lead 2+, they have bisulfate in there. And what's going to happen with the bisulfate is it's going to precipitate out the lead as lead sulfate. You see that? Here. And so that's one of the reasons you need sulfuric acid in there. You also need sulfuric acid in there because when the lead 4 oxides reduce, we're going to reduce it to lead 2. But when we reduce it to lead 2, we're going to precipitate it out as the sulfate here as well. So kind of a similar strategy. Is this reaction going to be as easy to reverse? Well, if you look back at this reaction, is this reaction easy to reverse? No, it's not so easy to reverse, you know. The same thing with the other one here. But it turns out it's not so difficult to reverse, oddly enough. And if we reverse it, this is the reverse reaction here. We take 2 lead 2 sulfates. One is going to be oxidized, the other is going to be reduced. And so we have 2 of them. And so one is reduced to lead metal, the other is oxidized to lead 4. And so this is the reverse reaction. And the reverse reaction is non-spontaneous because the forward reaction is spontaneous, 2.02 volts. And so in order to reverse this, we're going to need more than 2.02 volts. This is that overpotential business too, to reverse it. Right? And it turns out car batteries are rechargeable because even though this doesn't look so reversible, it actually is. Whereas primary cells and secondary cells, maybe you could reverse this, but it'd be too difficult typically to reverse to get to the same thing. And so when we look at a car battery here, they're showing it 2 ways. Here. They're showing it in the discharge state. In the discharge state, we have the lead anode. And the lead anode is going to be black or red color. Black or red? Black. And the electrons are going to flow from the anode to the cathode. The cathode's red. And so the cathode gets positive, the anode gets negative. The anode is where we generate the electrons. The electrons are going to flow from the anode to the cathode. But it's always weird because when we think about the hot terminal, you know which one is the hot terminal? You think the hot terminal would be this one because that's where the electrons are being produced. But the hot terminal is where the electrons are being pulled in. And so the hot terminal is red here. This is the positive terminal here. However, when we recharge, so this is discharge, the electrons go through the external circuit to the cathode. When we recharge this, we force the electrons to go backwards. When we force electrons to go backwards, then this is no longer the cathode. This will now be the anode. And we're going to force these electrons over here, and this is no longer going to be the anode. Now it's going to be the cathode. And so we're going to take the lead 2s and deposit it as lead. Do you think we're going to deposit in this pristine matrix? No, it's not going to look so pretty. And each time you do this, it looks less and less pretty because of entropy. Right? And so there's going to be a maximum life. And it depends on how much material. So some batteries last 1 year, some batteries last 5 years. And if you buy a 5-year battery, it's going to cost you a lot more than a 1-year battery. That depends on how many cycles you can get out of it, recharge cycles. So it's nice to have a replaceable battery like in a car, but in a phone, I guess you can't really replace a battery, fortunately. So this is the button cell here. Again, zinc. Zinc is cheap, and it's used as the anode. So it's a zinc anode. And what's the oxidizer here? The cathode is the steel case, but the oxidizer is, yeah, the silver oxide paste. That's the oxidizer. Silver ions are a good oxidizer. And again, you try to have as many solids as possible. Look at this reaction. Solid, 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 solid. What does that tell you? It's this, the voltage is going to be stable. The voltage, the cell voltage is what, 1.8 volts? Yeah. Get 2 of them, you can get over 6 volts. This one is a good reaction to reverse. This one's easily reversible. So nickel cadmium batteries are secondary cells. Secondary cells we could recharge. And so this reaction turns out to be reversible. But again, solid, solid, liquid, solid, solid. You see that? So that's why the reactions look so weird. You get that. This is 1.4 volts. And then we have the lithium-ion battery here. This is totally different, though. Yeah. Totally different. We build up a separation of charge. So we build up positive charge over here at the negative electrode, and we build up positive charge over here. I mean, negative charge over here. Separation of charge is going to create the voltage. And this is intercalation. There are a whole bunch of polymer batteries that kind of do the same thing. You know. And so you could read more. But this is intercalation. It's a sandwich material. And so it's a little different. There's reserve batteries, which are these dehydrated batteries. Just add water. So this is your dehydrated battery. Just add water. You add water, then it comes to life. So the voltage is 0 volts until it comes into contact with a solution containing ions. Actually, if you add just water, DI water, it's not going to be so great. You want salt water. Create the salt bridge. So ocean water would be good. This is a fuel cell here. A fuel cell, in theory, will never run out of fuel. And the oxidizer is cheap. It's oxygen, and you can get that for free from air. The reducer here is expensive, and it is hydrogen gas. And what you can have is you can have an electric car that generates electricity on demand. If you have an electric car that generates electricity on demand, do you need a whole bunch of batteries? Do you need like 1,000 pounds worth of batteries? No. But you need somewhere to store the hydrogen. There's also methane fuel cells. You can use any fuel cell. Any good reducing agent will work. But right now, the cars that they have are the Toyota Mirai. Have you heard of that one? And the Mercedes had one too. I forgot what that was called, the Mercedes something. And the problem is storing hydrogen. It's a gas, so you don't get as much energy density. You know what has the highest energy density are like hydrocarbons, gasoline. Gasoline has a lot of kilojoules packed in a small volume. Whereas hydrogen, even if you liquefy it, and so you have liquid hydrogen, it doesn't have as much energy. And so you need much bigger storage, and you need very high pressures. Not only that, having extremely high pressure hydrogen is very scary because hydrogen is, combustible. So it forms a very metastable mixture in air that can quickly react if there's heat around to form a gigantic fire or fireball. But I guess it's the same thing, you know, if you have like a Tesla. Have you seen there's some video on YouTube where they crash a truck into a Tesla? It just erupts into a big fireball. And they crash a truck into a bunch of other cars. See what the survivability is. And so either way, they have to generate safer ways of storing this, you know, high chemical potential energy mixtures. But the fuel cell is promising here if there's cheap ways to generate hydrogen. So people are looking at cheaper ways, and they have all different kinds of hydrogen. Have you heard of the different kinds of hydrogen? There's green hydrogen, purple hydrogen, red hydrogen. Have you heard that? In Chem 1A? Okay. I don't know if I want to be this. Gray hydrogen is made from natural gas. Blue hydrogen is also made from natural gas, but by a different process where they capture the carbon. Natural gas leads to carbon emission. And so to improve that process, they capture the carbon emission. Green hydrogen is produced by electrolysis. And unfortunately, the electrolysis rig isn't set up, but we can electrolyze water. So this is good, except you need electricity. And where does electricity come from? Electricity usually comes from burning methane. Burning methane means more carbon, and more carbon means more carbon tax, and more greenhouse gases and that kind of stuff. Black hydrogen comes from coal. Pink hydrogen comes from electrolysis, but the electricity comes from nuclear. So compare electricity from burning methane or natural gas versus electricity produced from nuclear. Electricity produced from nuclear is thought of as carbon, what they call it, carbon neutral, or no footprint, no carbon footprint. Turquoise hydrogen comes from natural gas straight, not by burning it, but pyrolysis of natural gas. Pyrolysis just means you break apart natural gas molecules at high temperature. And then yellow hydrogen. Yellow hydrogen, this is very promising, solar. So what would be cool is if somebody could develop solar cells that are very efficient at electrolyzing water just using solar energy. So if you have like solar cells on the top of your car, and then you can fill your car with water and then electrolyze it using solar power. In fact, my friend at UCSB was into this. You know, he was into developing solar cells that would be efficient at making hydrogen. Yeah. But it's not there yet, unfortunately. There's another type of hydrogen that is pink, but it's made by a different process. There are two nuclear processes, and one of these nuclear processes is apparently very promising. And this is being developed in Japan, where they're using a different kind of reactor. It's a molten, what was it? Molten sodium reactor, and they can produce hydrogen very efficiently that way. And so they're looking at that. And so maybe the infrastructure will be there. I mean, the infrastructure really isn't there for electric cars yet, and it's not there for hydrogen yet. I think it's going to take some time to develop, of course. But there are a lot of people working on this. Not just like UCLA, there are people working on this. At UCSB, there are people working on this. And so, a bunch of schools. And so fuel cells are very promising. Yeah. But there's definitely detractors. You can use any fuel, hydrogen, methane. Methane fuel cell vehicles and hydrogen fuel cell vehicles are already on the road. And in Torrance, I think there are 2 hydrogen filling stations, one on 190th and one on Prairie or Madrona. And then there's some methane. Methane can do combustion as well. You don't have to generate electricity. You can just burn the stuff. Methane's much cleaner burning than gasoline. Okay, then we have air batteries. Those are fuel cells. Air batteries, just air in, air out. That's the oxidizer. And we have aluminum. So fuel cells are air batteries as well. But in this air battery, the aluminum's fixed. You can't go to the gasoline station and refill with aluminum. Once the aluminum's gone, then your air battery's dead. And you're going to have to figure out a way to refill it with aluminum or just throw it away and buy a new one. All right, let's stop here. And then yeah, let's take a break for 15 or so. There's one final section of chapter 19. I don't know if I'm going to cover it today. The final section is electrochemical stoichiometry. And we just introduced new conversion factors. That's it. A little bit about the lab. So one of the things we like to do is we like to do the two-pronged approach. The two-pronged approach I talked about near the beginning of the semester, but two-pronged meaning what? Yeah, kind of the theoretical and empirical. So we talked about what makes an acid strong, and there are multiple factors that play into acid strength. So that's kind of theoretical, things like polarity, bond energy, this kind of stuff. And then we try to correlate it with the data, experimental data, the actual bond energies, the actual polarity. But what we want to do is we want to connect it with some things that we can actually measure and see, because we want to try to be as quantitative as possible. And so one of the techniques, this is an extremely powerful tool that's used in organic, but in all kinds of chemistry. It doesn't have to be organic. It can be medicine too. There's a nuclear magnetic resonance spectroscopy. In medicine, it's MRI, magnetic resonance imaging, but the theory is the same. And so what we can do is we can observe the hydrogens. And, if we look at ethanol, the hydrogens are different. Like the methyl hydrogens are different than the methylene hydrogen, which is different than the hydrogen on the oxygen, obviously because in the structure it's different, but can you actually see it? Well, we can see it if we have like a crystal structure of this, or if we have a model of this, but can we see it in other ways, experimentally? And it turns out we can see it experimentally in other ways. One of the ways is nuclear magnetic resonance, because hydrogen, the nucleus of a hydrogen acts like a little magnet. Electrons act like a magnet too. And so electrons have what's called a magnetic moment. And so electrons can have either the North Pole up or the North Pole down. And then there's a very famous experiment, the Stern-Gerlach experiment, where Stern and Gerlach shot silver atoms through a magnet. And then like half the silver atoms were deflected up, and the other half of the silver atoms were deflected down, because there's a random distribution of North Pole up and North Pole down. And so we'd have two. And so that was one of the early experiments. This is back in the quantum chapter. Do you guys remember quantum chapter? Electron spin is called the first quantum number, second quantum number, third quantum number? The fourth quantum number, yeah. It's typically called the fourth, and it's plus 1/2 or minus 1/2, and the Stern-Gerlach nailed it, It's either plus 1/2 if it gets deflected one way, or minus 1/2 if it gets deflected the other way. Now, electrons are pretty powerful magnets compared to the proton and the hydrogen. The proton and the hydrogen is a very weak magnet, and so it's much harder to see. In fact, the first people to try to observe the magnet, the electron, that Stern-Gerlach was done pretty early, I think, in the 20th century. But in the 1950s, a group of physicists tried to observe the spin of the nucleus of a hydrogen, and it could either be, there's two quantum states, either up or down, for the nucleus of a hydrogen atom. But it's so weak that the electronics, the amplifiers, weren't strong enough. And then 10 years later, in the 1960s, electronics have improved dramatically. And another group of physicists, the first group didn't, but another group of physicists used more sophisticated electronics, and then they were able to observe that, the two spin states of the hydrogen. And they call it the same, plus 1/2 and minus 1/2. The plus 1/2 and minus 1/2, that comes from the Schrodinger equation. So it's kind of odd. You're thinking, why call it plus 1/2 and minus 1/2? But it's because of the mathematics of the Schrodinger equation. That's the actual number it comes out to. It turns out that that's called a magnetic dipole. A magnetic dipole is either North Pole or South Pole up. But there are more complicated nuclei that have what are called quadrupoles. And quadrupoles will have multiple North Poles and multiple South Poles. And so it's weird. But these hydrogen atoms act like little magnets. And you can observe these little magnets by, what you do is you place them into a gigantic magnet. You place them into, you think a gigantic magnet would be like the Earth's magnetic field. The Earth's magnetic field is a gigantic magnet. And geologists can, interestingly enough, geologists can see if the solidified lava moved at all, because what they do is they look at all the little frozen magnets in solidified lava, which are contained in the nuclei, and they see, is it aligned with the Earth's magnetic field or not? And if it's aligned, then They say, well, it hasn't moved since it's solidified. But if it's misaligned, then it must have moved somehow, or the Earth's magnetic field moved. But anyway, you put these into a giant magnet, and then what you do is, when you put it into a giant magnet, let's say the giant magnet has north pole up, then what's more favorable? Parallel spin or opposite spin? Usually opposite spin is more favored. You would think. Opposite spin should be more favored because then the two spin states can be paired and it would be diamagnetic for electrons. But what does Hund's rule say? Hund's rule says that when you fill energetically degenerate orbitals, you fill them one at a time with opposite spin or with parallel spin. It turns out parallel spin is better, and what's better depends on the distance. So if the two magnets are very far apart, then it's random. There's no preferred orientation. It's totally random. As you bring them closer, the two magnets, then parallel spin. But if you get them too close, then opposite spin. And so opposite spin is better. And so it depends on the size. It turns out like nickel, cobalt, iron, nickel, cobalt are just the right size that parallel spin's good. And so what you could do in iron, nickel, and cobalt is you can get all the spins in the atoms to line up and make an even more powerful magnet. Because if all the north poles are lined up, then we have that. That's called a ferromagnetic material. So you had diamagnetic, opposite, paramagnetic, parallel, and ferromagnetic, a whole bunch of parallel spins. It's ferromagnetic. But anyway, what happens is these hydrogen magnets like to line up with the giant magnet. And so they like to be parallel with the giant magnet. Well, if they line up with the giant magnet, then what you can do is you can shine light photons on that and flip them, because in order to flip them, it goes a little higher in energy. And so it would be parallel, and then you hit it with a photon, and it flips, and then it goes anti-parallel. Anti-parallel is a little bit higher in energy than parallel. When it gets hit, well, what kind of photon do you need? And so in nuclear magnetic resonance, you don't need gamma ray photons. You don't need X-ray photons. There are no X-rays involved here. You know what you need? Radio wave photons. So radio wave photons will flip it. And so you just shine radio waves at it and then flip it. Well, then we can see some are harder to flip than others depending on the environment it's in. And so some of these are harder to flip than others. And so what we can see is we can separate them based on the energy that it takes to flip the spins. And so this is just flipping spins. So nuclear magnetic resonance is playing with magnets. So if you've ever played with magnets, you're doing it quantitatively. Can you tell which hydrogen this is? You can tell based on the structure of the peak. So this is what we call a singlet. This is a quartet. There are 4 peaks here. You can resolve them better if you just spread it out. This is called a triplet. This is a triplet here. And those peaks form when adjacent hydrogens interact. So the hydrogens on one carbon will interact with the hydrogens on an adjacent carbon. And so it depends on how many hydrogens are on the adjacent carbon. And then you can see, you're just playing with the magnets and seeing how they interact. And so it turns out this one, we can tell which hydrogen that is, and we can tell what hydrogen this is. And there are different ways. Another way is we can integrate the area under the curve. That is, we can just determine, this is called an integral here. And this tells us how much area is under the curve. And this one looks like twice as much, and this one has about 3 times as much the area. Do you see that? And so this is going to be the alcohol based on the integral. This will be the methylene hydrogens, and this will be the methyl hydrogens here. And the reason they split like this is the methyl hydrogens interact with the methylene hydrogens. There are two methylene hydrogens, so it gets split into 2 plus 1, 3. And these are the methylene. The methylene are going to interact with these primarily. We got 3 of them here. And it's going to be 3 plus 1, so it gives us a quartet. And so we can determine. This is a fine structure. The fine structure is breaking it down. So the thing we're going to look at here primarily is this. What causes the shifts here? This is called a chemical shift. And these numbers here are the chemical shift for that. And we call this downfield. So we start at 0 here and work our way downfield, and this is called upfield. So the methyl are pretty far upfield, whereas the hydroxyl proton's pretty far downfield. The methylene's somewhere in between. That chemical shift gives us some important information here, and in NMR, and that's one of the main things we'll look at in NMR spectroscopy. So NMR, as it is abbreviated by scientists, is a phenomenon which occurs when the nuclei of certain atoms are immersed in a static magnetic field and exposed to an oscillating electromagnetic field. So you put it in a giant magnet, and then you hit it with radio waves. Some nuclei experience this phenomenon, and others do not. It depends. Not all nuclei are spin 1/2. So deuterium is spin 0. So deuterium nuclei don't even act like magnets at all. So deuterium are invisible in magnetic resonance and nuclear magnetic resonance. There are a bunch of nuclei that are invisible. And not only that, they have different frequencies. So it depends on what radio waves you hit it. And so what you can do is you can image the hydrogens, like in water, or you can image carbon. But it turns out carbon-12 is invisible. Only carbon-13 is visible. Carbon-12 has spin 0. And so, of course, you want a theory that tells you what spin the nuclei are going to have. And I think the particle physicists, they say they can predict that kind of stuff. But I don't know the theory well enough to understand how they predict it. But we don't have to in order to use it. So spectroscopy is just the interaction of light with matter. And so we're looking at the radio wave. Radio waves are kind of low energy. That's enough. What we want, though, is you want stronger and stronger magnets. Because if you have stronger and stronger magnets, then it makes a big difference whether it's parallel or anti-parallel. And you get better signal. And so right now, they're trying to build. And so the question was about the coil. Right now, they have a coil of wire. And when the electrons move through a coil, it generates a magnetic field. And so what they're doing is they're using a superconducting coil. And that generates the biggest magnetic fields possible. But still, they're trying to get bigger magnetic fields. They're always trying to get bigger magnetic fields. Because you'll get better signal to noise. And so this is just a review of electromagnetic radiation. And then we come to spin properties here. Spin is a fundamental property of nature like electrical charge or mass. Spin is a measure of the angular momentum, rotation about an axis, hence the term. Spin comes in multiples of 1/2. 0, 1/2, 1, 3/2, 2. Any spin greater than 1/2 is quadrupolar and can be plus or minus something. Plus or minus 1/2, plus or minus 1, etc. Protons, electrons, and neutrons possess spin. Individual unpaired electrons, protons, and neutrons each possess spin of 1/2. Etc. And so this is a little bit of the observations. You see patterns. Atoms with an odd number of protons will have spin. Atoms with an odd number of neutrons will have spin, but atoms with an odd number of both protons and neutrons will have spin. Atoms with an even number of both protons and neutrons will not have spin. So why is that? They just cancel each other out. So you look at the observations, you look for patterns, and then you try to come up with some hypotheses in engine theory. This stuff we don't really need. So the most common is hydrogen. Hydrogen is very abundant. It's like 99.9 something percent abundant. Deuterium is not very abundant, so even if it's invisible, we don't really care. P31 is 100% abundant, but it has a weak signal, so unfortunately it's spin 1/2. Sodium-23 is not as abundant as sodium-22. Nitrogen-15, nitrogen-14, yeah, is okay, but the spin is kind of weird. This is spin 1. Carbon-13 is good, except its abundance is very low. It's 1%, and so it gives a very weak signal. Fluorine-19 is okay as well. But the most common is hydrogen. So if we try to visualize the nucleus of hydrogen, it's like a little magnet here. And that's some fundamental property of the proton. And it's going to have two spin states. It's going to have two spin states when we put it into an external magnetic field. It's either going to be parallel or it's going to be anti-parallel. If it's slightly off, then it's going to go to one or the other. And so they act like little bar magnets. If there's no external magnetic field, then we don't know which way's up, which way's down. And so they're just going to have some random orientation. And so there's no external magnetic field. They're just going to be randomly oriented if they're far enough apart. If they're far enough apart, they're going to be random. If they get closer, what's going to happen? They go parallel, and if they get too close, they go anti-parallel. And so they're kind of far apart, and this is random oriented. Now we put those hydrogen atoms in a giant magnet. This is what's going to happen. We put it in a giant magnet, and the preferred orientation is parallel. But some are still going to be anti-parallel because not all the hydrogens will have the same energy. We're going to have a distribution of energies, right? And so this is why they want big magnets. The bigger the magnets, the more difference there is in energy. So the bigger the magnet, the bigger the difference it makes whether you're parallel or anti-parallel. And so with a weak magnet, it barely makes a difference. Whether you're parallel or anti-parallel, it's hard to detect the signal. But with a bigger difference, you're going to get a clearer signal because there's going to be a larger difference in the energy. Does that make sense? That is, it's much more favorable to be parallel than to be anti-parallel. And so it depends on the external magnetic field strength, which we call B naught. The bigger the B naught, the better. This is why the magnets are huge, and they're superconductors. So we can take a look at a magnet here. These are superconducting magnets, so they have to be kept extremely cold. So this is like a typical size of a magnet here. Oh. Oh, I know why. I think. I gotta end this slideshow then. This is like the typical size. This is actually a little bit. No, actually, that's about the right size. This is just a gigantic magnet. Most of this volume is filled with liquid nitrogen. And then in the center of this magnet, it's filled with liquid helium. And you have to get the metal really cold so it can superconduct, because metals, they vibrate. Their lattice vibrates. And those vibrations means electrons will have more resistance in going from one end of the metal to the other. And so if you can cool down the metal to where it's barely moving, then the electrons can move quite freely. And we'll hit a temperature where it superconducts. And so these are extremely cold, but it's pretty well insulated, so that person's not terribly cold. But this is just magnet and electronics. The thing is once you get this superconducting, you can just unplug it. You just need to plug it in just to get the electrons moving, but once electrons start moving, you're good. Until if you let the liquid helium level get too low, then you're going to quench the magnet. If you quench the magnet, this is disastrous. And so there's people on daily duty maintaining the magnetic field. Daily to fill with nitrogen, and probably weekly to fill with helium. So the bigger the magnet, the better signal we're going to get. So the external magnetic field is represented by this blue arrow, and the proton, the nucleus, is represented by this. This is a little magnet of the nucleus here. So it's either spin, we call it spin up, North Pole up, or spin down, North Pole down. And there's going to be a difference in energy here. Most of the population will be at lower energy. You know, when we turn on the external magnetic, if there's no external magnetic field, then it doesn't matter. There's no right side up. But when we turn on the magnetic field, then some will make it up here because we have a distribution, you know, the Maxwell-Boltzmann distribution, basically, energies. This will be, but there will be a population difference. That population difference is what we're measuring, because what we're going to do is we're going to excite some of these lower energy ones to higher energy by flipping the spin using radio waves. So there's a lot of physics involved here with gyroscopic precession or precessing spin. So this is a precessing spin here. We're not going to worry about the physics of this. What we are going to worry about is the strength of the magnetic field. The stronger the magnetic field, the bigger the difference in energy of the spin state. So we want bigger because it's going to give us a better signal. But even the biggest ones are still small. You know? And so it says, and is always very small. The spin, the difference in energy between the two spin states is always very small, but the bigger the better. Because if it's very close together like this, it's hard to measure the difference in energy. This is still all in the radio waves. And so we flip the spin. This is spin flipping here. And here, boom, to here. And the spins are preset. This is called precession here. And so this is just showing it inverting. Hit it with RF. RF is radio frequency. Hit it with RF, boom, flip some spins. Measure the absorption of radio waves. And then you get the energy spectrum for that. Depends on how much money you have. These are about the frequency of energy that it takes to flip the spin. So if you're low budget, well, if you take organic chemistry here, we're low budget. We don't have a superconducting magnet here. We have a permanent magnet, but it's a really good magnet. It's like a cobalt nickel alloy magnet, which has a field strength of about 1.4 Tesla, which translates to about 60 megahertz. Megahertz is radio wave, 60 megahertz to flip. But you don't get quite the same resolution as you would, you know, if you had something like a 9.56 Tesla. Tesla is a unit of magnetic field strength. A 9.56 Tesla magnet, which would increase the frequency to 400 megahertz. There's a much higher energy transition here. You get much better resolution. But 400, it used to be 400 megahertz is at the cutting edge of technology. But now 400 megahertz is kind of the normal magnet. After the earthquake, Santa Monica got a 200 megahertz magnet. But their magnet requires a lot of maintenance because that's a superconducting. Our magnet doesn't require much maintenance. It just sits there. However, the electronics of the NMR do require maintenance, and unfortunately the electronics of the NMR are damaged. We have to upgrade the computer and upgrade some of the other components, and we don't unfortunately have enough money to do that, and so the NMR is just dead, sitting in the lab over there next door. But it's one of the most powerful tools in organic chemistry for structural analysis. In MRIs, they're all looking at the same proton. In MRIs, they're looking at hydrogen atoms in water. And there's lots of water in your body. But they all kind of resonate at the same frequency. So what they want to do is they want to do this. For NMR, you want what's called a homogeneous magnetic field. Because if you have an inhomogeneous magnetic field, what it does is it broadens the absorption peak. And the wider the absorption peak, the poorer the resolution. We want to narrow the absorption peak to make better resolution. In MRI, they don't want a homogeneous magnet. They want a non-homogeneous magnet that has a gradient like this. So when you go into an MRI, one end has a smaller field, the other end has a bigger field. And so all the hydrogens in water are going to resonate at a different frequency depending on the field strength. And so in an MRI, you lay down in this giant magnet, and the giant magnet has a gradient like this, so that you can pinpoint, depending on what frequency the magnet flips, that it resonates, we call it resonance, then that'll tell you where you are in three-dimensional space. And so they can pinpoint where you are based on the frequency. But for us, we're just looking at what energy it resonates at. And so this is the absorption peak here. And the stronger the magnet, the narrower this is. The weaker the magnet, the broader this is. So we like that high resolution better, but it comes at a cost. So we have a very homogeneous magnetic field, and not all the hydrogens absorb the same energy. But you think, shouldn't the hydrogens all absorb the same energy? They all have a proton. And the answer is no, they don't, because it depends on what they're bonded to. Taking a proton and bonding it to things will change its nucleus. Does it change the nucleus? No, it doesn't really change the nucleus because, you know, in chemistry, chemists don't really worry too much about the nucleus because we mess with it so much. What does it change? Chemists are more worried about the charge. Charge being positive, negative, or delta minus, delta plus. Charge is what's most important. This is why I might have wrote some comments on your exam, because a lot of you have the habit of not writing any charge on. And if you don't write a charge, that's very bad in chemistry because, that's all we care about is the charge. That's why redox reactions are so energetic. Redox reactions are so energetic because the charge makes a huge difference. But so try to get in the habit of writing the charge. Whenever you write an ion out, you want to write the charge. In Chem 1A and Chem 4, I was very strict about it, but in Chem 1B, I not. In Chem 4 and Chem 1A, I took off a lot of points, but I didn't take off any points, I think. Just try to get in the habit of doing the charges. Okay, the reason is because of something called diamagnetic shielding. Electrons act like magnets, and proton, the nucleus, acts like a little magnet. And so we're playing with three magnets, essentially. We have the external magnetic field, we have the magnetic field generated by the electron cloud, and we have the magnetic field generated by the nucleus. Now, how do these magnetic fields interact? Something interesting happens with the electron magnetic field. The electron magnetic field is much stronger than the nuclei's magnetic field. And so why should the proton nuclei in different compounds behave differently in the NMR experiment? The answer to this question lies with the electrons surrounding the proton in covalent compounds and ions. Since electrons are charged particles, they move in response to the external magnetic field. So we have this external magnetic field which is going to cause the electrons to move, so as to generate a secondary field that opposes the much stronger applied field. So the weird thing that happens is if we have the electrons here, then they're going to generate a response opposing this field and hence weakening it. And that weakening of that field is called shielding. So the electrons shield this. So if you're this nucleus here, you're not going to feel as much of the external field because you got all this electron cloud around you. And so that's very important here, shielding. And so this is why we call it diamagnetic shielding. The secondary field shields the nucleus from the applied field, so that B naught must be increased in order to achieve resonance absorption of RF energy. Thus, B naught must be increased to compensate for the induced shielding effect. When an atom is placed in a magnetic field, its electrons circulate about the direction of the applied magnetic field. This circulation causes a small magnetic field of the nucleus, which opposes it. And so this is the map if you want to do that. But we are not even going to bother with that. All we're going to do is this. This is a free proton. A free proton doesn't have any electrons around it. It's completely unshielded. And so this proton is going to interact directly with the magnetic field. So it's going to feel the full strength of the magnetic field. These protons up here are more heavily shielded. The protons up here are more heavily shielded because they got an electron cloud around it. And so it depends on how thick the electron cloud is around the hydrogen. And so, for example, here, you can, actually, this is backwards. Sorry, this is backwards from what I was just saying. Ignore that proton over there. But one of the things is you can de-shield this. How do you de-shield it? Well, is there a way to polarize the electron cloud? Normally you have a symmetric electron cloud, but you can have an asymmetric electron cloud by polarizing it. And you polarize it by what? Bonding what to it? So we can polarize the electron cloud by bonding the hydrogen to something. And if that something is more electronegative, then there's going to be a tug of war for the electron cloud, and who's going to win? The more electronegative element. And so the more polar the bond is, the less shielded. The more nonpolar the bond is, the more shielded. And so it depends on the bond polarity. So this gives us a way of measuring the bond polarity, because we can measure polarity. When we measure polarity, but we measure the net polarity. And so I didn't even talk about this in Chem 1A, but there's a unit called dBi. Have you heard of the dBi? dBi is the magnetic the dipole moment, not the magnetic moment, the dipole moment of the molecule. But the dipole moment of the molecule is the sum of all the bond dipoles in 3 dimensions. And we can measure that. But the thing is, we need to separate it. But this gives us a direct way of measuring the polarity of the bond for the hydrogen. And what did we say acid strength depends on? What was one of the factors that acid strength depends on? It depends on the bond strength. The weaker the bond, the stronger the acid. But it also depends on the stability of the conjugate base. It also depends on, this is why carbon, the carbon-hydrogen bond is only like 350 kilojoules per mole. The oxygen-hydrogen bond is like 430 kilojoules per mole. Oxygen-hydrogen bond is actually stronger. So why don't we take the hydrogen from the carbon? Why do we take the hydrogen from the oxygen? Yeah, and acid-base reactions are positive, negative. Bases are negative, acids are positive. So the more polar the bond is, the more acidic it should be. And we could measure the polarity of the bond by looking at the shielding. So for example here, we can take a look at 2 examples. More shielding, that is a more dense cloud, is going to result in the external magnetic field. In this case, they're calling it H naught rather than B naught. It doesn't matter. Those are both symbols for that. Is going to depend on the shielding. If you look at the shielding component is quite big, which lowers the external magnetic field, so we have H effective, the effective. And we can see that the energy is lower. This is increasing frequency this way, so increasing energy this way. So this absorbs a lower energy. So the more shielded it is, the lower energy it absorbs. Okay, the less shielded, so if we strip away some of the electron cloud here, then we have less shielding. Less shielding means it'll see more of the external magnetic field, and so it shifts the frequency. This is called chemical shift. Well, this isn't. The chemical shift is, at what energy it absorbs. And different things will have different chemical shifts. And so which one is going to be more shielded? A carbon hydrogen or oxygen hydrogen? Which is going to be more shielded? Hydrogen bonded to carbon or hydrogen bonded to oxygen? Carbon. And so this is less polar. In fact, that's what we call non-polar bond. Very little distortion in the electron cloud. Whereas here, this is a much more polar bond. And so oxygen is much more electronegative. It's going to suck the electron cloud from hydrogen. Well, if it sucks the electron cloud from hydrogen, then that hydrogen here feels or experiences more of the external magnetic field. If that hydrogen experiences more of the magnetic field, then it's going to absorb at a higher energy. And therefore, its chemical shift is going to be different. So the chemical shift of this hydrogen will be different, and then we can tell the difference between the 2 hydrogens because they're going to have 2 different chemical shifts. So here's some examples of this. So over here we have, this is called tetra, what are these? Methyl. Tetra, methyl, and this is silicon. So we call this tetramethylsilane, or TMS. TMS is usually where we set the 0, because this is about as shielded as you're going to get. It's fairly nonpolar. And so we call this 0, the most upfield. And so everything else will be positive going this way. It's kind of weird. And then going this way, everything will be negative. So there are things that are even more shielded than TMS, but TMS is about the most shielded that we're going to deal with. And so we set our spectrometer to 0, so we calibrate this here. And then we measure it in parts per million. And so here, this would be 1 ppm, 2 ppm, 3 ppm. And we can see that the different hydrogens absorb at different. This one's going to be more shielded or less shielded? Less shielded. And so this is going to be farther downfield. The farther downfield we go, the less shielded it is, the more polar it is. And so we can see how polar things are. You know, the more electron withdrawing, you know, this is what we call it, this is kind of an interesting one. We have 3 chloros there, and then we have this carbonyl, carbon-oxygen double bond. And benzene rings are somewhat electron withdrawing. And then we got a bunch of chloros on there. And so we look at these. Delta is the shift. This is the chemical shift. And delta we read in units of ppm. This is TMS is our standard. This is our reference. This is an arbitrary 0. So we just set this at 0 ppm and then measure how many. So this is 126 hertz. This is 313 hertz. 432 hertz from TMS. And NMR is very sensitive, so we can measure these very precisely, as long as the peaks are quite narrow. And so we're going to do that. So the lab I had lined up is this. But we don't have much time for the lab, unfortunately. Let me quantum mechanical programs can calculate chemical shifts, because this is all quantum mechanics, this shielding stuff and all that. And so if I had a program like Max Spartan, I can ask Max Spartan to calculate the theoretical chemical shift. And so my idea for the lab was I wanted to look at the experimental chemical shifts and compare that to the pKa. So we're just going to look at the acid hydrogen on the carboxylic acid group and determine how polar that is, you know, how big the delta plus is, by looking at the chemical shift. And the further downfield it is, the more polar it is, right? Based on that. And so this paper was published in Springer Nature in 2018. Springer is not the official Nature magazine. Nature magazine's a huge journal. I don't know how they got away with calling it Nature, but it's okay. Correlations between the proton, which is H1, NMR chemical shieldings, and the pKa values of organic acids and amines. And so if we read the abstract, the acid dissociation constants and proton NMR chemical shieldings of organic compounds are important properties that have attracted much research interest. However, few studies have explored the relationship between these two properties. In this work, we theoretically studied the NMR chemical shifts of a series of carboxylic acids and amines in the gas phase and in aqueous solution. It was found that the negative logarithms of the experimental acid dissociation constants, i.e. the pKa values, of the organic acids and the means in aqueous solution correlate almost linearly with the corresponding calculated NMR chemical shieldings. Key factors that affect the theoretically predicted pKa values are discussed in this paper. The present work provides a new way to predict pKa values of organic and biochemical compounds. So, of course, we want to be able to understand it well enough so we can make predictions. Like, if I drew a structure of an acid that I wanted to make, could you predict the pKa value? Let's say I wanted a higher pKa value or a lower pKa value. I'd like to know what that is, if I could. And so they have a bunch of pKa values. And so these pKa values here are experimental pKa values. And I'd like to correlate the experimental pKa values with the experimental chemical shifts, but these guys are theoreticians, so they didn't do that. they correlated the experimental pKa values with the theoretical chemical shifts. Their first attempt at correlating the pKa values with the theoretical chemical shift was not very successful. Let's take a look at the data. Take a look at the R squared values here. Oh. Shoot. Forgot to end the slideshow. All right, this is what I was reading. Sorry, I thought you were reading along with me. So this is published by Springer Nature, 2018. And what they're trying to do is they're trying to correlate the chemical shielding with the pKa, which makes sense because chemical shielding is correlated with polarity. Some key words here: proton NMR chemical shieldings or chemical shifts, pKa organic acid amines, and linear correlation. So the introduction gives us some background. You know, amines and organic acids play crucial roles in numerous chemical and biological processes, etc. So it gives us a little bit general interest stuff and why somebody might be interested in this. You know. They actually go through a pretty long intro because they talk about some of the historical work that's already been done here. And this is a computational, this is not a wet lab. And so this is a theoretical paper, so they talk about the computational details rather than the experimental section, methods and materials. They talk about how they calculated the NMR chemical shifts. They calculated using this type of quantum mechanics over here. And this is the correlation they got. So on the left, they have the experimental pKa values, vertical axis. On the horizontal axis, they have the calculated theoretical chemical shifts, or chemical shieldings. Actually, this is related to chemical shifts are in parts per million. This is chemical shieldings. And they got an R squared of 0.03. Does that look pretty good to you? That's complete. Would you say that there is some kind of correlation? Well, this is much better. This is 0.03. They got 0.25. This is way better. But is 0.25 a good correlation? No. These are the organic acids. These are amines. Amines can act as acids, depending on which proton you pluck off. So amines are actually amphoteric. Did you know ammonia is amphoteric? Ammonia can lose a proton and make amide, or ammonia can gain a proton and make ammonium. So amines are typically amphoteric. And if that's the case, we can do this. So the amines look to be better correlated than the carboxylic acids here. But would you publish that? No, that looks like garbage, the correlation.
Yeah.
And so they thought, why is the correlation so bad? And what they did here is, in the quantum mechanics, it's not so easy. So what they did here was they did a gas phase correlation. Gas phase correlation is just looking at the polarity, the de-shielding of the proton. But there are other things that interact. So when we look at what makes an acid strong, there are multiple factors. And how do you weigh those? Do you weigh them evenly, or do you bias it towards some and versus others? And so sometimes it's very tricky. And so then what they did was they tried different things here. And so let's read this, 2A, 2B. Correlations between experimental pKa values and calculated proton NMR shieldings for A, organic acids, B, amines, complexed with explicit water molecules. So what they decided to do here was they decided to model the acid in like a sphere of water, or explicit. Explicit could just be one water molecule. And so they threw in one water molecule there, which is the solvent. And they got a much better improvement. Look at the correlation here now, 0.5 and 0.74, but are these any good? No, these are still not good. And so the results in discussion, they're talking about all their data. Correlations between experimental pKa and calculated proton NMR shieldings. They used higher level models, and then they used this IEFPCM solvation model. So what they did now was they solvated the acid with a sphere. I guess the previous one, they just put one water molecule there and had that interact. But now they have a sphere of water molecules around here. And is the correlation better? Yeah. Correlation is getting better. But now look at this. Now they're letting the water molecules do their thing. And look at the correlation. That's pretty good. It's not great. I mean, we want more 9s, but it's pretty good. You know? So definitely polarity has an impact on pKa. And it looks like there are other effects here. Well, polarity, of course there's other effects. Hydration, waters of hydration. You know, if we ignore the waters of hydration, then the correlation was really bad, right? And so the conclusion here, normally in a short paper we don't have a conclusion, but a series of quantum mechanical calculations were performed on 20 organic acids and 24 amines to explore the correlation between their theoretical proton NMR chemical shieldings and their experimental pKa. I want to see experimental chemical shieldings, not theoretical. That would be good. So that was the purpose of our lab. The purpose of our lab was I was going to dig out the experimental NMR chemical shieldings and then see how that correlates. The experimental ones would be based on the chemical shifts. But I didn't have enough time to do it. And so we're just taking a survey. And so this is kind of research. They're just taking observations and then they're coming up with these hypotheses. But basically, the end result was they got a decent correlation if they incorporated the water solvation effects, hydration effects. So there are multiple factors influencing this kind of stuff. And they only looked at 20 acids. I wanted to look at many more acids than this. And so in the conclusion, we could say that we're going to, in conclusion, we want to talk about the future. We'll incorporate experimental values and look at a lot more acids. And so El Camino is starting a data science program, so I was thinking of asking some of the data science people to come up with a lot more data for us to analyze and then see if we can see the correlations a little bit better. But this is typical. We don't have enough time to go to the computer lab, but you can go to the computer lab to work on your synthesis report. You know, are you making some progress on the synthesis report? You know, in the results and discussion, like here, they're trying to, you know, talk about the correlation and what improves the correlation and the steps they did to improve the correlation. But in our results and discussion, you want to talk about the synthesis, why you think you have what you have, that kind of thing. So our results and discussion will have chemical equations. You know, here in the appendices, I'm sure they have lots of data. Actually, they don't show the data here. Okay, but anyway, nuclear, if you're going on to organic chemistry, you need to know NMR, and you need to know it very well, probably by the second semester of organic chemistry. So I wanted to introduce it here. And there's another technique you need to know very well, and that's IR. And so the other correlation we're going to look at, which is the next paper, And the second part of this lab is the vibrations. The vibrations are going to depend on how polar that bond is, and we can actually measure the vibrational energy, and so we can see where it vibrates. In fact, here, since I have a few minutes left. Oh yeah, I need to give you your test back.
Let's say I'm a biology student working on a research paper for school. As I work, I incorporate research from websites to support my ideas. And it's crucial that I cite these resources to maintain the integrity of my work. With the Grammarly browser extension enabled, I click the Get Citation button while on a website I reference. Grammarly instantly generates a fully formatted. I even have my citation formatted in various styles like APA, MLA, or Chicago.
Another ad.
Fourier transform infrared spectroscopy, or FTIR, is an analytical technology.
Sorry, the volume's low, but you could just look at the pictures.
To understand the structure of molecules and the composition of molecular mixtures. FTIR spectroscopy uses modulated mid-infrared energy to interrogate a sample. The infrared light is absorbed at specific frequencies directly related to the atom-to-atom vibrational bond energies in the molecule. When the bond energy of the vibration and the energy of the mid-infrared light are equivalent, the bond can absorb that energy. Different bonds in a molecule vibrate at different energies, and therefore absorb different wavelengths of the IR radiation. The position or frequency and intensity of these individual absorption bands contribute to the overall spectrum, creating a characteristic arrhythmic of the molecule. Since FTIR spectroscopy produces signals that are specific to the type of molecular bonds or functional groups, it is the ideal tool to measure the making and breaking of chemical bonds during reaction. Coupling FTIR spectroscopy with attenuated total reflectance, or ATR, increases the utility of this technology by providing a means to monitor reactions in situ and in real time. Measurements via ATR and FTIR.
Well, anyway, that's kind of the vibrations. The vibrations are going to depend on the bond.
Impossible to determine in real time.
So we can measure the vibrational energies. And the vibrational energies will depend on the polarity as well. But let me just input this, and then I'll give you your exam back. Do this. All right, Nicole. Hannah. Okay, Zane. Colin. Okay, Mitchell. All right, that's it for today. Pretty much. If you have any questions on this, I'll try to input more scores in for the labs. Usually the labs will bring people up. I don't grade those too critically. And the homework, unless you have a lot. If you have a lot of homework missing, you can still turn it in to get points. Do that, but make sure you get the labs in. And then I'll try to update the labs over this weekend. Thanks.
Thank you.
Thanks. Yeah. Oh, that's right. That is.
Number 4.
Uh-huh.
Why is the optimum pH for the NH3 NH4 plus buffer 9.26?
Because the optimum pH is equal to pKa. And what's the pKa for NH4 plus?
I need the pKa for NH3.
Oh yeah, pK for NH3, because the acid is going to be NH4 plus and the base will be NH3. So you can't use the pKa for NH3. So that's the reason why. The HCl and with NaH, because it's strong acid. Strong acid and strong base don't make a buffer. It makes a neutral salt. It would be if it were buffer. You would be right, but it's not a buffer, so it doesn't work. It has to be a buffer for that to work. Because that's based on the Henderson-Hasselbalch equation. No. The 1-to-1 is the optimum pH. The highest capacity means the most concentrated. Oh, yeah, you're welcome. Thanks. Have a nice Thanksgiving again. I was going to try to keep it short today, but I ended up talking the whole time. Sorry. I think you can sit through that. But we're we caught up. Okay, thanks. See ya Monday.